Okay, you should now be able to see my screen, also in Zoom. So yeah, welcome also from my side. My name is Jannis Klinkenberg. I'm working here in the HPC group, and I will present different talks today. So one is about CLAIX and the multi-GPU setup that we have here. The other talk will be about TensorFlow and distributed training in TensorFlow. So starting, we are currently working with our CLAIX 2023 setup. So you here see the new branding of our system. But I will directly jump into the details here. So basically the system consists of mainly 3 segments. So we have the segment HPC, which basically consists of CPU-only nodes. So we have about 630 of those. These are 2 socket systems with Intel CPUs, 48 cores each, so each socket. So we have 96 cores in total. These also have local SSDs, and we have different configurations that we see here, basically with different amount of main memory. So the large share has 256 gigabytes of memory. Then we have some share that has 512, and then we have 2 very large nodes that have 1 terabyte of memory. The second segment, then that's the interesting part for our focus here in this workshop, is the ML segment, the machine learning segment, where we have 52 GPU nodes. So basically it's the same configuration with the, as the CPU-only nodes, but we have additionally 4 NVIDIA H100 GPUs that have 94 gigabytes of HBM2E memory. Also interesting here is, I don't very much like that, but we have a little bit less local SSD storage, and we come to that in a second, or at least today we will talk about that, compared to the CPU storages, but we have here consistently 512 gigabytes of main memory, which is pretty good. So you can do a lot combining this 512 gigabytes with the GPU memory on the NVIDIA H100s. So these are our main segments. Then we have a third segment that might also be interesting for you, but it's not really batch-like usage of the system. It's the interactive segment. So of course we have our lock-in nodes where you can already test a few codes or basically set up all your stuff before you go into batch. But sometimes it's also interesting that you, for example, use JupyterLab or something like that. So interactive working with notebooks. And there we have a dedicated, these are a few nodes, like 2 or 4 nodes, dedicated nodes with smaller GPUs that are especially utilized for Jupyter Hub usage. Good. What else can I talk about the system? So the system is of course interconnected. So all the nodes are connected, all the storages are connected. And here we have an InfiniBand NDR network. So it's a high performance network that is not really comparable with the classical Ethernet that you have at home. Yeah? So it's much more performant, much faster, and all these nodes are connected to each other. Additionally connected, we have storages. So we have 3 types of storages. We will also have a look at that a little bit more tomorrow about the different storages, about the pros and cons that each storage has. But in principle, we have 3. We have our Lustre file system, which is a highly parallel file system that can be used with multi-node, multi-process jobs. And we have a lot of quota there. Then we have quite new, so it basically was installed 2 weeks ago or so. We have the GPFS, where we have our home and work system. So one is backup, the other one is not. And we have Beyond, which is an on-demand file system where you can basically use the local SSD storage of the compute nodes in your job. So it's basically an on-demand file system that is created for your job and then will disappear afterwards again. But this is basically not accessing network resources, but local SSDs in your job. Good. So let's have a little closer look at the GPU nodes. So basically we see here on the right-hand side a sketch of the GPU nodes. So these are two socket systems. These are internally on the CPU side, again, split into different NUMA domains, but that's not very important here. However, we can see we have 4 GPU nodes, and each GPU is connected to a different place in the system. So here, for example, GPU is connected to NUMA domain 0, then 1 is connected to 2, 3 is connected to 4, 2 is connected to 4, and 3 is connected to 6. Yeah? So basically each socket has a direct connection to 2 of these GPUs, and the GPUs itself are again connected with each other with a higher bandwidth connection. As I said, we have 96 cores in total. Subnuma clustering is enabled, which is not super important here. 512 gigabytes of memory and these 4 H100 GPUs. Good. So how does that work if you now submit a job and you want to use 1 GPU? So the point here is the system allows shared usage. So basically, if you run a 1 GPU node, 1 GPU job, then other people are also allowed to use the rest of the system. Yeah. So in principle, there could be 4 1 GPU node jobs on each node running at the same time. The point then is how to split the shared resources. So there's main memory of 512 gigabytes and we have 96 cores. So in principle, the idea is we split that by 4. So if you use 1 GPU, by default, you get 1/4, so 25% of the system. Yeah, so that also has a certain effect on billing. So that means if you have a compute project, then a certain amount of quota is subtracted from your compute project. Yeah, and here a small example for billing. Yeah, case you have 1 GPU, you basically get billed for 25% of the resources, cores and memory. That means if you don't specify anything special and you request 1 GPU, you get 24 cores and you get billed for 24 core hours. That's our billing unit. And you get 25% of the memory. Yeah. Same thing goes if you use 2 GPUs on a system, you get basically billed for 50% of the memory. So you always have these packs of 1 GPU and 24 cores. Although it's also possible if you specify something else, for example, I only want to use 5 cores, yeah, you only are able to use 5 cores in your job, but you get still billed for 24, yeah, because this is the shared resource for 1 GPU. Good. So now the question is how to use these GPU nodes, and first of all, we need to allocate them. Yeah? But I will first go into the usage. We will also have 2 more talks about that in terms of PyTorch and TensorFlow. But first of all, some general consideration. Yeah? So and basically, if I want to use those GPU nodes and I have multiple of those, there are different options. Yeah? The first option is that I have one process that is serving multiple GPUs. Yeah? So basically, each process takes care of communicating with, so one process is taking care of communicating with each of the GPUs. Yeah? And there might also be other nodes that have the same configuration, so there needs to be some communication. But typically, if I only focus on this part, so a single GPU node, then this is a scenario that you could choose. Yeah? For example, if you do not scale beyond 4 GPUs, then this is a good starting point. Yeah? We have, of course, different use cases. So classical use cases where I will not go into too much detail, which is, for example, MPI plus CUDA, MPI plus OMP target. So we will basically look at those cases here, PyTorch, TensorFlow, and there are also options for that configuration. Another configuration is basically a little bit different. So basically each process gets 1 GPU. And this is, for example, quite common in PyTorch. In TensorFlow, there are different configurations, as we will see later. But basically here, the idea is each process only looks at 1 GPU and sends data to it, uses for training. And there's some communication happening between the processes, for example, to exchange weights, to handle the data splitting, that you say, okay, 25% of the data is done by this process and this GPU, and so on and so on. Okay, so as I said, we will look at practical examples later in PyTorch as well as TensorFlow. But first, now the question is how to request GPUs, and we partially did that already yesterday in the bring your own code. But here just a few examples. Yeah? So we have our batch script, and we have these as-batch flags that we can specify to request resources, to specify what we actually need. So here, very simple example, I want to have a batch job that goes for 15 minutes. I want to use our partition C23G, which is the GPU partition, the ML partition. I want to have one node, one process per node. So in principle, that results in one process overall. I want to use 24 CPUs per task, which is the cores per process. So I basically have this pack of one GPU and 24 cores. And I want to have one GPU and one GPU per node. So this is the grest flag. We often see gres on our system, but it's also possible to use something else, which is called GPUs per node, which is a little bit more expressive and actually tells what is happening. Yeah, basically the same thing. And then later in the script, I basically have my execution commands, so running Python scripts, accessing the GPU, training models, stuff like that. Yeah? So basically, this is my template of a batch script, and then I have on the command line, I just need to submit that to the Slurm scheduler, and this will then take care of scheduling the job on the node. Yeah? So this is basically my resource description. Now let's look at the assigned resources. I get one GPU, I get 24 cores. So basically that's 25% of everything and 128 gigabytes of memory. Yeah, so on the billing, if I spend 1 hour in such a job, I get billed for 24 core hours. If I spend 10 hours for this job, I have 240. Even if I use only one core in this setup, I still get billed for 24. So if there are any questions in between, just let me know. Yeah, I will just go forward and present a few different cases. Yeah, so here this is the setup: single GPU node, single GPU job, one node, one process. Then we have multi-GPU node, multi-GPU job. So one node, one process, but basically the idea is to access multiple GPUs. Yeah? So basically all this stuff stays the same, but I here say I want to have GPUs per node too. Yeah? So basically I get a job on one node and I have two GPUs in that job. Yeah? So on the billing part, I then also get two GPUs. Yeah? So here I set CPUs per task 48 because I want to basically be able to access the 48 cores that I anyways get built, although I might not use all of them. Yeah? And on the billing part, of course, then it increases from 24 to 48 because I now use 50% of the resources. So there might be different configurations. For example, here we had n tasks per node, so I have one process. I might also want to use the setup where each process is servicing one GPU. So basically the only thing that increases is here n tasks per node equals 2, and each gets 24 cores. Basically same setup, but I have two processes, and I can, for example, use MPI to launch two processes at the same time, and each one is basically just seeing one GPU. Yeah, so same thing here, two nodes, two processes. So I basically just increase the number of nodes. And here I say I want to have 4 GPUs per node. So I basically use two nodes, two full nodes, 4 GPUs per node, so in total 8 GPUs. Yeah, so basically this is what I get here, 8 GPUs, all cores on the systems, all memory on the two systems, and I also get billed for the complete two systems. And then a different configuration here. So here I had basically one node again. So one process on each node is servicing all 4 GPUs. And here I basically said I want to have 4 processes per node. So basically 1 per GPU. So I have 2 full nodes again. Each GPU is serviced by 1 single process, but I have the same resource configuration. So I use the complete node, 100% of everything. But I have one-to-one mappings between processes and GPUs. Good. Now, exception. Yeah, so these were pretty regular cases. Now the exception. Yeah, for example, I only want to use 1 GPU, but I want to have more memory. Yeah, for example, 128 is not enough for me. I can still do that. So I can basically say GPU, 1 process, I want to have 1 GPU, but now I say I want to have more memory. So my process or my memory per node is, that is the flag here, is increasing. Yeah? So basically the assigned resources, you see that here on the right-hand side, are changing. Yeah? So I have 25% of the resources on the node in terms of cores and GPU, but now I have more memory. Yeah? That means that other users cannot get their share of memory and you get billed 50%. Yeah? So extreme case is a job is requesting 1 CPU of the 96 and requesting all memory. So basically no other user can basically use anything on the system or execute anything on the system because you have all the resources, all the shared resources. Yeah, so still possible to do that, but I would recommend not to use that flag unless you really, really need that. Okay, so these were just some examples how to allocate GPU resources, how to specify your requirements. And again, I would highly recommend not to use that because basically if you request the right amount of resources, Slurm will allocate the memory for you in the right manner. But there are certain corner cases where you actually need more memory per core than you currently have. Yeah? And this is where you need to specify that. Otherwise, don't use memory flags. Okay, thank you.